So this cup holder, right, water bottle holder, it's being held up by 2 screws, right? You could also use hot glue, or I was thinking about using these Velcro strips that I have. They're rated for 15 pounds, right? And obviously this bottle of water is not 15 pounds when it's full. However, it is not, this is assuming you have whatever you're hanging flushed against the wall, but we have some kind of distance right there, right? We have a distance between the wall and the bottle. It's hanging off a ledge or a shelf. So what we got to do is calculate not only the force being exerted from the bottle by gravity, but the distance from that center of mass to the wall. So what we got to do first is calculate the mass of the bottle. I mean the force of the bottle, which is of course mass times acceleration. The mass being the bottle itself is 591 milliliters, and water is 1 gram per milliliter, and we're going to ignore the mass of the plastic. So that's 591 grams. Converted to kilograms is 0.591 kilograms. And then acceleration, being of course gravity, is 9.81 meters per second squared. All right, now the thing is, this, when we multiply these two together, 0.591 kilograms times 9.81 meters per second squared, we get, shoot, I think it was like 0.591 times 9.81, 5.8 newtons, right? Because kilograms times meters over second squared, that's newtons, right? So that's 5.81 newtons. That's the amount of force that we need to hold just the bottle up, right? But that's not accounting for the distance between the center of mass of that bottle and the wall that it's hanging off of. So to do that, we're going to calculate the torque. Torque is, of course, force times displacement. We have the force already right here. We just got to calculate the displacement. And the displacement is from the wall, where it's hanging off of, and the center of mass. So that center of mass from the wall distance is actually I think it was 40 millimeters. So 0.04 meters, right? Calculating those together, we get 0.232 Newton meters, because we're calculating units as well. Meters times newtons, Newton meters. So this is the torque, right? This is the torque being exerted on the wall right now from that bottle. So furthermore, we're also ignoring the mass of the plastic of the 3D printed plastic as well, because yeah, I'm a professional. Furthermore, so now we're gonna have, now that we have the torque, right? We have the torque, we gotta find the force, the max shear force of the Velcro that we have. So to do that, we have the force of the Velcro, and that's gonna equal to the torque being exerted on it divided by the height of the Velcro, okay? So we have the torque right here. We just got to measure the height of that Velcro, and I already did. It was 20 millimeters. So that is 0.02 meters. That's the Velcro, right? So then we go 0.232 Newton meters divided by 0.02 meters. And of course, these are the same units being divided by each other, so they go ahead and cancel out. And then after dividing that number by 0.02, we end up with 11.6 newtons. And of course, we don't really measure things here in the States with newtons. We do pounds. So to convert that into pounds, we go 11.6 newtons divided by multiplied by 0.225 pounds feet over newtons if my pen decides to work, giving us 2.6 pounds. So this is the amount, this is the strength. That's the force that the Velcro itself needs to hold, right? To hold up the, yeah, this is rated for 15 pounds, so it's definitely going to be able to hold it. However, that's not accounting for the strength of the adhesive. We don't know if this adhesive is going to be either as strong, less strong, or stronger than the Velcro, depending on what it's being adhered to. So that is a separate calculation that I needed to do that I just realized right now. But Yeah,